Welcome to the Knowledge Graphs seminar. We hope to learn a few things about how AI should explicitly represent knowledge. The seminar is co-organized by myself, Vinay, Naren, and Mike. The motivation for the seminar was that we are seeing the use of knowledge graphs in a variety of applications, including web search, for answering questions, and for data integration. We are also seeing that knowledge graphs are mentioned in many papers in natural language processing, computer vision, and more generally in machine learning papers, where people have started to use knowledge graphs as a way to store information which is learned or extracted by these algorithms. National Science Foundation has also recognized the importance of knowledge graphs, and they've recently launched a new program called Convergence Accelerator, as part of which they are funding about 21 new projects that make use of knowledge graphs in a variety of ways. This seminar series has a structure to it. We will start by asking some very simple and basic questions like, what is a knowledge graph? How do we go about creating it? And then we will get into how do we reason with it? How do we make use of it? How do we evolve it over a period of time? And then we will also look at how we use the knowledge graph in conjunction with modern AI algorithms. What are some high value use cases of knowledge graphs? And towards the end of the series, we will ask the question, what are some of the open research challenges that need to be addressed on knowledge graphs? The design of the seminar series is that each session is structured as a panel of 3 individuals. And we put in a lot of thought to invite individuals who would bring in a very different perspective. In general, we have tried to mix perspectives which come from traditional knowledge representation and database systems with online data or knowledge curation, with more recent work on machine learning and natural language processing. Each participant will start with a presentation of not more than 30 minutes. And we are hoping that we will be left with about 20 minutes at the end to engage in discussions. Personally, from my point of view, it's very interesting to hear what these participants with different perspectives have to say to each other, because these perspectives seem to be meeting using knowledge graphs. During the seminar, if you have any questions, please type them in the QA box. We will be monitoring the QA box, and we hope to take up those questions during the discussion period. For Stanford students, the attendance at today's session is not required. From the remaining 9 sessions, they can attend any 8 sessions to get a credit for the course. And as I said previously, we are recording the session, but recording is only available to Stanford students. Today, we are happy to have with us Danny, Hans, and Michael. I'm not going to spend reading their illustrious resumes to you, because resumes are on the website, and I like us to just get started with their presentations. So our first presentation will be by Danny. Danny, over to you.
Thank you for the intro to the session. Let me get everything started. So, do you see the presentation?
Yes.
Perfect. Okay. So I want to start with a few basic things. What are knowledge graphs? How are they useful, and so on. And I want to do this through a story. So this is the city of Winterthur in Switzerland. Quite a beautiful little picturesque city. And around 2005, person from Winterthur, Manuel Sichel, has started working on the Wikipedia article on Winterthur. And he has been active on it since then, actually. So now for 15 years, working on the article and working on the history, working on the politics of it, and so on, editing the page throughout the time. One of the topics he has been working on was the list of sister cities of Winterthur. So he added the 4 sister cities that he knew of, two in Switzerland, another in Czech Republic, one in Austria. Now, this here is the city of Ontario, California. It's about less than an hour away with the car from Los Angeles, particularly given the traffic currently. The thing is, in around 2006, 2007, someone went to the Ontario, California article and added the list of sister cities here. And one of the sister cities, as it was added, was Winterthur. Now, sister cities are supposed to be reciprocal. So if you're a sister city with one city, the other city should be a sister city with you. But there was nothing in Wikipedia, obviously, because it's just text that would inform the editors on the Winterthur article that there is some inconsistency in the text, that that something happened that made Wikipedia itself being inconsistent. And Manuel, although he was really interested in information like this, for a whole decade he wouldn't see this inconsistency. It would be in Wikipedia and no one would notice it. How come? Well, it's because knowledge in natural language can easily remain hidden. It's very, very easy to bury knowledge inside of natural language. If you have a lot of text, if you have big archives, there can be a lot of useful knowledge, but it's just not always actionable. And we'll get actually to a few of those examples later. Then came Wikidata. What is Wikidata? Wikidata is an open knowledge graph. It launched in 2012, and just like all the other projects of Wikimedia, anyone can edit it. Its main goal is to support Wikipedia, but it has since grown out of that. It provides structured linked data about a lot of interesting topics in the world, and is licensed under CC0, which means basically public domain, and anyone can use it for any purpose. You can see down there the early funders of Wikidata. Among them Google, my current employer, the Gordon Betty Moore Foundation, the AI2 Institute, Yandex, and also IBM Watson. With Watson, actually, we got the prize money from the Jeopardy game, and when they won Jeopardy with IBM Watson. If you haven't seen this because you're too young, you should take a look. It's quite a nice example of AI research in the last decade. How does Wikidata look like? So in Wikidata, we have a page like this. This is the page about Ontario, California. So we see on the right-hand side the list of all Wikipedias that have an article on Wikipedia, and it's all put together here. We see up here in the center, we see the different labels in different languages. So we see that Ontario is called in the languages we can see here, all Ontario, with a short description of what it means. The important thing is that for Wikidata, Ontario is actually not Ontario. Ontario is ambiguous. It could be the city in California, but it also could be a province of Canada, and it could be many other things which are called Ontario. For Wikidata, this thing is identified with this Q identifier, Q488134. That's what means Ontario for Wikidata. The interesting thing now is if you look at Wikidata, you can then take the whole user interface and switch all those description and labels from one language to another. So instead of looking at it in English, as we do right now, we can also look at it in Russian, for example. We can look at it in a Hindi language. We can look at it in Hebrew. So, and the nice thing is, you're not just looking at it in that language. It's actually as editable as in any other language. And if someone comes in and edits in the Hebrew Wikipedia fact, it will be immediately visible, the difference in the Russian Wikipedia, in the Chinese, in the Chinese Wikidata, in English Wikidata, and so on. Because it's only a single knowledge graph for all the languages, unlike the Wikipedias, which are all independently from each other. Okay, back to English. The main part of Wikidata are the statements down here. And we'll take a closer look at these. What we see here is a statement, and what it's basically saying is that this page that we're talking about, Ontario, California, has a property called Twin Administrative Body with the value winter tour. And if we think a little bit more abstract of it, try to abstract from how it's represented in the page, what we see here is there's an entity for Ontario, a node, a thing, a topic that represents the city of Ontario, and one that represents the city of Winterthur. And between that, we have an edge connecting those two, and the edge is labeled, in that case, with Twin Administrative Body, which subsumes also sister cities. So in reality, as said, we actually, this is not how it looks like. We have those Q identifiers. We say Q488134 has a P190 labeled edge to the node Q9125. But to make it a little bit simpler, we use the English labels for these things to read it for us. Obviously, if you would be, you could also have it all labeled in Chinese or German or whatever you prefer. Now, every page in Wikidata represents a node, and those links between it represent edges. And if you think about it like this, then you get a graph. So you have a lot of nodes, you have a lot of edges there. So we can zoom out. Basically, we can take a little bit the neighborhood of Ontario and Winterthur and see what cities are they twinned with, and we get a graph like this. We can zoom out further and get an even larger graph and further. And these are all cities connected through the Twin Administrative Entity link. And in the end, actually in Wikidata, we have about 16,884 nodes being connected by almost 45,000 edges. So this is a pretty big graph now, describing all the different sister cities of the world. But Wikidata doesn't only have sister cities. This is one possible label for the edges that Wikidata has. We can actually go and look at different bits and see how it would look if we would look at all the entities and their edges and labels. So now we suddenly have also entities that represent people. They have nodes that represent people. We have nodes that represent stadiums and so on. And they are linked with different labels to the city, for example. We have place of birth, we have location between them. And again, we can zoom out and we get this large graph with labeled edges. And this, in its core, is a knowledge graph. This is the Wikidata knowledge graph. This is a small part of the Wikidata knowledge graph. The whole Wikidata knowledge graph actually contains more than 80 million nodes about all kinds of things, about genes, proteins, viruses, cities, people, species, and so on and so on. And they're connected by more than 1 billion edges. In fact, we crossed the billion just last week, and I'm happy to announce here that we're now more than 1 billion edges in Wikidata. So it's a pretty large knowledge graph which you have here. The W3C, the standardization organization that's also standardizing standards like HTML and so on, has created standards to share this kind of knowledge graphs, this kind of graphs, and the main of them is RDF. What RDF does is basically, so we have Wikidata, and you can publish on the web in RDF standard this kind of graph, which Wikidata does. And in RDF, it looks, for example, like this. This is just like this little graph that we see here. And basically you say, well, we have subject, predicate, object, which means like one node is connected by this property with that object. And this way, we publish this large RDF graph in Wikidata. Now the thing is, Wikidata is not the only thing that publishes large RDF graphs. The Library of Congress, for example, also publishes a large RDF graph with a lot of entities and so on, also in RDF. And now the thing is, okay, so we have the one knowledge graph published by the Library of Congress. We have a knowledge graph published by Wikidata. Now, what we have in Wikidata is also saying, well, Q9125, Winterthur, is connected to N5001388 in the Library of Congress. And it basically says, well, this is the same thing really, but those two identifiers are about the same real world entity. And if you want them, you can basically say, okay, let's treat them as just one node basically in our knowledge graph. And suddenly you merge the 18 million entities from the Library of Congress with the 80 million entities from Wikidata, and you got an even larger graph with more connections, with more knowledge, and that you can explore across the different graphs. And you don't only have Wikidata and Library of Congress and then those labels, but actually, if you look at this, what Wikidata has, it provides a kind of a translation from Wikidata to the Library of Congress to natural languages. And this makes it a kind of modern Rosetta Stone, where we say identifiers here mean the same thing as the identifiers there, means the same thing as the names and description that we have here in the language. And in fact, what Wikidata connects is more than 4,800 different catalogs, like the Library of Congress, like the Getty catalog, like the MoMA catalog, and so on, that connects them to all these different catalogs out there in 414 natural languages where you can also bring together. So you have a huge selection of data, a lot of it authoritative data coming from archives, coming from national libraries, coming from museums, universities, and so on about certain topics. So you have these huge libraries and catalogs that you can all connect together and create a huge knowledge graph out of this. And then we still don't stop. We have something called schema.org, which provides vocabulary, which provides labels for edges, basically, that you can use to publish even more data on the web in an openly decentralized manner. And what you get then is that you have more than 12 million publishers out there who publish a lot of the data, a lot of triples using schema.org annotations that you can, that are also published, that are also translatable in IDF that you can directly use in your knowledge graphs. In fact, more than 31% of the web contain schema.org annotations. So a large part of the web that you're browsing today has is part of the linked open data cloud and can be merged into a huge, gigantic graph of triples out there. Datacommons.org is a project that was recently started by Google, where you can get hold of some of this data being mapped to even more data sources, and you can then use it in different ways. The nice thing about knowledge graphs, as we have seen, is that they are kind of easily composable. So we have all these different knowledge graphs, a little knowledge graph on each website. We have the big knowledge graph like Library of Congress, like Wikidata, and you can pull them together. If you know which nodes mean the same thing, mean the same entity for your purposes, you can merge them together. And if you know how the properties, the label edges, the label of the edges are related to each other formally, you can also make inference on them and to understand together how they all belong together. And that, when you get this huge, large knowledge graph, you can end up easily with trillions of triples, literally, and hundreds of millions of entities describing all kinds of things in the world. So what? Okay, so we have huge amount of triples, but what can we do with that? What's the point? Well, the thing is, now that you have that you have your own knowledge graph, that you pull together all the triples that you're interested in, that you put them into storage, what you can do is now you can create a triple pattern. You can say, okay, I want to match any node that has a labeled edge that's labeled, for example, with place of birth, P19 in Wikidata language, to winter tour. And what you would get now is basically every node whose place of birth is in winter tour, which means basically everyone who was born in winter tour. We can extend the pattern and say, okay, I also want the place of death of those nodes. And then I want the coordinates of the place of death of the nodes who have a place of birth connected with winter tour. And you can start building this kind of large query patterns, of graph patterns. And then you have then you have graph databases that can actually use those patterns and return you the results of those. And for example, if you do this in Wikidata, with a pattern like this, with a graph query like this, I can usually take those coordinates and then put, for example, the coordinates on a map. Without any single coding, I get now a list of, I see now a map of all the places where people that are in Wikipedia, because they're in Wikidata, so people that are in Wikidata that are born in Winterthur, where have they died on a map? And without writing a single line of code, I can get this query result directly out of Wikidata. Now, looking at this pattern, just to see how powerful this is, I can switch, for example, place of death and place of birth. And now I already changed it in the query, okay, people who have died in Winterthur, what are the coordinates of the places where they were born? And again, I can get a nice map of those. So people who moved to Winterthur, where have they been born? It's super simple to do this kind of things. If you think how you would do that before Wikidata, it would have been quite challenging to actually get this kind of results. Now you can just write a query and get the results back within seconds. Before that, I mean, the information was available, right? You could just go to Wikipedia, you could go through all the people who linked to Winterthur, see how they are linked to it, and create those lists, create those maps. It would be possible, obviously, but it would have taken quite a bit of effort. Today, go ahead, write a query, get the results back. One way to, the standard to write those queries, those graph patterns is called Sparkle. And taking a graph pattern like this, it looks a lot like the RDF that we've seen before. So we have variables marked with question marks, then we have the labels that I use. And basically what we see here is a direct translation of the graph pattern above. And this is the query that you can use verbatim on Wikidata in order to get the locations back, and then use that to create the map out of the Wikidata query engine. Sparkle is used quite extensively in Wikidata. We have about 8.5 million Sparkle queries that I ask every single day, which is much more than I had ever expected. And the nice thing about the Sparkle endpoint, as you have seen, we can also create those visualizations directly out of the Sparkle endpoint and then embed the result in external contexts or in other ones. So what we have is just a few examples of such queries. We can create a gallery of paintings by Picasso, or an interactive timeline of cities in California and when they have been founded, where you can scroll, zoom, and so on. Causes of death of people inside of Wikipedia shown as a bubble chart. How often do certain causes of death appear and so on. Populations of countries bordering Germany. Again, you just get those queries into the system. You can query, you get a visualization. Those are things that you usually wouldn't find in a book because they are often too specific. So here you can interactively create those queries, create those visualizations, and get them out of Wikidata. Country flags depicting a sun. We have all the country flags in Wikidata. They're often annotated with what they are showing. And here we can just ask for a gallery of those flags. The pictures themselves are taken from Wikimedia Commons, which is also connected to Wikidata. So we can actually just pull those together from different sources. I love this example. It doesn't look like much, but it's actually showing really nicely the power of the federated querying that I was talking about, making the graph bigger than just Wikidata. So this query shows us the location of ATMs around the city of Munich that are connected to certain banking networks. Now, Wikidata doesn't have every single ATM in it, and will never have that because ATMs are not particularly interesting. But there are other data sources that have ATMs, and they are marked up with the banking, in particular geolinked data, which is taken from OpenStreetMaps. So we have geolinked data, and they have a Sparkle endpoint. Then we have Wikidata, where we have the information which banks belong to which banking networks. And then we have OpenStreetMaps with the actual map that we can use for rendering. So what the Sparkle query endpoint of Wikidata does Again, this is just a single query. There's no coding involved or anything. You can directly type into the Sparkle endpoint, give me all the banks that are related to the banking networks I'm interested in. Now get from GeoLink data all the ATMs that are attached with those banks, get their coordinates, and then render all of this on OpenStreetMaps in a map. And this is, if you think about what you're doing there, connecting all these different data sources on the fly to generate a map like this, that's just always up to date based on the idea, is pretty powerful and done quite simply. A few other examples. This is the list of heads of state sorted by the Erdős number. This is my academic genealogy. So you see my PhD supervisors, then you see their PhD supervisors, and so on and so on. All of this just directly taken out of Wikidata. This is the etymology of the word water in different languages. The interesting part here is that knowledge graphs often are focused on ontological information, but we extended Wikidata to also provide lexicographical data about words, not just about concepts and ideas, and how those words are connected to each other. And what we have here is a lot of etymological data, for example, about words. We also have the different forms that those words have and so on. And this has been started only a year ago and it's grown quite well since then. And finally, a map of the sister cities of Winterthur. And this was literally the query that Manuel Sichel was asking Wikidata. So it has been more than 10 years since he has started working on Wikipedia. And in the meanwhile, Manuel has actually become a member of the city council of Winterthur. And at some point, he was actually interested in creating a map of the sister cities of Winterthur, just to be able to show it, to print it out and use it in some material. But when he queried Wikidata for this, when he wrote a query and got the map, he noticed, oh wait, what's this thing over here? He never knew about Ontario, California being a sister city. And being on the city council, he should probably know. So he checked and he thought, well, it's probably just an error. He looked into Wikidata and he saw, oh, this data was taken from the Wikipedia page. Okay, so he went to the Wikipedia page and he thought maybe some error there. He saw it was entered there like almost 10 years ago. And he looked, but there was actually a reference to it. So it's probably not just some vandalism or some error in the editing. And the reference was pointing directly to the official website of Ontario. So he went to the official website of Ontario, since the source was given for this information, and lo and behold, there it was. It listed Winterthur as the sister city of Ontario. He was a bit surprised because in Winterthur they didn't know about it. He actually asked city administration, being a councilman, he asked the city administration, do they know anything about this? And he said, no. He asked the city archives if they have anything about this. The city archive came and looked and came back with the answer, no, we've never heard about it. So he wrote an official letter to Ontario asking, hey, what's going on? Why are you listing Winterthur? And they answered him that back in the 80s, the Winterthur mayor came to some meeting of mayors in California, and he and the mayor of Ontario hit it right off, became good friends, became good buddies, and decided to make the cities sister cities, which also went into their respective city councils, which was approved and implemented. Now with the information of when this happened and what actually happened, the archives were totally able to produce those, the documents that they had on this. And before that, even though they were asked specifically, they wouldn't know it. So this is another example of how with a lot of documents, with a lot of natural language, you can hide information very effectively. Even when you need it, you can't get to the right information at this point. But once it's maybe actionable, once it's made into structured data available for querying, we see people actually going in, using it for visualizations, using it for tools, and this surfaces the data, makes it visible. And the more you use your data, the higher the quality of it is, and the more actionable this information becomes.
And then we have 5 minutes.
Thanks. Then what happens now is that indeed, thanks to Wikidata, Winterthur found its long-lost fifth partner city, and they rekindled the sister city relationship, and it's now back again, and everything is going fine. So, what can we learn from that? So first, nobody really cares about sister cities. And second, as said, it's really, really easy to hide knowledge in natural language. Making it structured, making it accessible in a way that machines can process it, make knowledge much more easier to access and to find, and to have it available at the moment when you need it. So trying to summarize the talk and also give a little bit of outlook of the rest of the seminar. So the big advantage of knowledge graphs are that they're comparably easy to compose. Unlike, for example, databases, which you can't just throw together and hope to get more magic out of, more oomph out of this, you can take several knowledge graphs and put them together comparably easy. You need to know which nodes are mapping to each other in the given, for your given use cases and so on. But all of this has solutions. They allow for inferencing, which means you can do actually smarter things. So if you know that something is a city, you also know it's a location. If you know that something is a sister city, you also know it's a twin administrative body, and you can map the different vocabularies between different graphs and so on to each other. I'm sure you will hear about inferencing much more than from this talk. There are trillions of edges readily available on the web, in different data sources, in different catalogs and so on, literally trillions of edges. So you can start your knowledge graph by taking as much knowledge as you need from the web, from open sources like these, or from other sources, and bring them together to build your knowledge graph and kick it off here. You can lift other data sources into graphs. Juan Sequeira, who will also speak here, has done a lot of work on actually taking classical databases and turning them to knowledge graphs so we can easily combine them. Knowledge graphs are comparably easy to edit, unlike, for example, machine learned models. You know how to actually, what the nodes mean. You can go in and actually edit, change them, and so on. You have, with graph patterns, quite a powerful query language to work on a knowledge graph. You have explainability because there's no magic happening. You have this graph, you have the patterns there, and you can go and pull it out. So you can actually kind of easy go and figure out what's going on and find why something is going the wrong way, or edit if something is missing. And we have standards for representing graphs and for representing graph patterns. So there's a lot of work already available that you can use when you have knowledge graph. Most importantly, I said that you can take something like Wikidata or those trillions and trillions of triples that are out on the web and just use them for your applications, build it internally or externally in projects, and have a lot of different use cases you can work with them. Thank you for your attention. So I try to ignore all the questions that came in during the talk. Sorry for that. Should we take some of the questions now, or should we just move on to the second speaker? How does this work?
Yeah, I propose we move to the second speaker and we'll deal with the questions at the end. So,
okay.
Hans, you are the next speaker. Hans, would you like?
Yeah, I'm unmuted.
Okay, well, you need to share your screen or slides.
Yeah. Can you see my screen?
Almost. Yeah, I can. Yeah, we can see your screen. Yes.
So, my name is Jans Aasman, the CEO of France Inc. And I'm going to talk about the knowledge graph work that we do. And before I begin, thanks, Danny, for the great introduction that you just did, because that will make my life a lot easier. So thanks. So very quickly, our company is a Lisp compiler company, but for the last 10 years, we've entirely focused on our semantic graph databases, the name AllegroGraph. And so we've been helping for the last 5 years companies build knowledge graphs. So today I'm going to keep it very simple, and Fine wanted me to mostly just give examples and demos, so I'll try to do that. a few text slides. So what is I'm going to talk what's in a knowledge graph, and then we'll look at some use cases that we're involved with. And I always say that there's kind of two kinds of knowledge graphs that I see. One are the knowledge graphs that are very much documented text-based and do a lot of natural language processing. And then the other ones are event-based knowledge graphs, where you just take enterprise data and put it into a knowledge graph. And I'm going to give you a demo of both of them. But to begin, what's in a modern knowledge graph? And then you kind of showed it already. Yeah, so to begin with, you have some form of a semantic graph database that allows you to put all these triples that Benny talked about in. You want it to be scalable because we're talking about trillions of triples ultimately. And in many cases, you also want to make sure if you use it in the enterprise that they're secure. And sometimes when it's a real-time database, you want it to even be ACID. So that's the first thing you want to be in there. Then in the ones that we built, ontologies and taxonomies are always there at the start. Yeah, if you can't agree on the definition of your objects or the concepts and the words that you're going to use, you're nowhere. So we always start with that. And then there's a lot of reasoning and rule-based processing involved, as you just saw. For the event-based knowledge graph, there's always silos information that need to be integrated. And up to here, it's all what I call old-fashioned AI, whereas a lot of people think that only machine learning currently is AI. But what I see in the knowledge graph that I listen to, I listen to the talks of people are the ones that we built. I would say in general, 70% is good old-fashioned AI, good old-fashioned knowledge representation, and the 30% is machine learning, advanced analytics, and more natural language processing and text classification. And recently, we even started going into knowledge graphs that get fed straight from speech recognition systems, and you can talk nowadays to them with chatbots. Now, as I said, we built several of these knowledge graph platforms. First that I'm going to demonstrate is about the famous Noam Chomsky. A group in San Francisco wanted to make sure that this about 1,000 articles and books will be with us forever. And so they started a project where the internet, the Internet Archive helped, we helped, Pool Party helped, and I'm going to demo that. We work with companies like Deloitte, where they where they take an entire bill of material of a car and put it into a knowledge graph, and then they link that knowledge graph with the knowledge graph of the logistic processes. So now you linked the parts of a car to the logistic processes, and that gets linked then to a knowledge graph about world news. So you try to figure out was there political unrest somewhere, or labor unions are striking, or there is horrible weather, and could it be that the place where you buy your stuff from is in one of those places and there might be a problem in your supply chain? So that is something we do. Then big projects we work on is for a call center, where we build a knowledge graph around the companies.
Your voice is going in and out. I wonder if there is something you could do at your end.
Let me check here.
It's breaking. I don't know whether it's the internet connection or.
It's all day my microphone was working really fine. Is it really bad? That bad?
I do not think it's the microphone. The microphone sounds to be fine. It's more some connection issue.
Yeah.
But Hans, we can understand you. It's just a little difficult, but it is workable.
It isn't workable? Okay.
It is workable. It is workable. It's not perfect, but it's acceptable.
All right. Okay. Then shall I just keep going?
All right. Yeah, let's keep going.
Yeah, sorry. Yeah. So help the call center to make the agents in the call center smarter by listening to how they talk to their customers, do NLP on the speech recognized text, and then give them real-time decision support using a knowledge graph. And then another project I'm going to talk about is what we do with the hospital in the Bronx in New York, where we have data of about 2 million patients and 10 years of data in a knowledge graph, and we can do all kinds of very, very interesting analytics on that data. So a very different type of knowledge graph. So let me just blow up the screen again. Let's see, can I get the big screen? Okay. So as I said, there's two types of knowledge graphs that we work on. One is the NLP-based, text-based, document-based knowledge graphs, and the other one is the entity, event-based one. So let me begin with the one about Noam Chomsky. Yeah. So as I said, there's about 1,000 articles and papers and books available. We want to make sure that we keep that forever. And we want to make it easy for journalists, students, researchers, strategists, and politicians to find his thoughts. And so we built a process around all this work. And before we did that, we had a group of people, mostly very politically interested people over 60, kind of in the hippie category like me, yeah, very interested in Noam Chomsky work, and built an entire taxonomy for all the important words in his text. And so here, for example, we have a concept of Vietnam War. Here's the preferred label. So the taxonomy always is about concepts that are language independent. Then you choose the preferred label for that in all the synonyms. And I could click on Cold War, proxy war, and then you would see that Vietnam War was a child of war, which is a child of hard power, which is a child of power. And anyway, so a big taxonomy with thousands and thousands of words can then be saved as an RDF file, as an RDF taxonomy, and loaded into a semantic graph database. And then you can do things like this. So let me start here, not this one, here. So here I have a client for a chocolate store, and I can look at the main classes that I have in this particular knowledge graph. And so I might have a book. Here's a few books. We have a much bigger version, but for the demo, I'll do this one. And I might have a book like media control. And the word media, and what we started with was a document that we chopped up then into a tree of paragraphs. And it goes roughly like this. You have a book that has a bunch of chapters. Then, so now we have the chapters. I can show it here. Then a chapter has paragraphs. So I'll show you a few of these paragraphs. And then these paragraphs have text. Yeah? So I could look at the content of one particular text. And here you see the text that you find in this book. This was actually about the last legal victory for labor was in 1935. Well, this is nice, but if you search and you want to give the whole paragraph, that might be too much. So we use some Python libraries, one from Gensim and one from Spacey, some tools that people use for natural language processing. Yeah, to create summaries. So for example, this is a short summary of the big text that you saw here. Let me step back. And then remember, we made this taxonomy of important concepts in the work of Noam Chomsky. We have a text. So then the next step, what we can do is you can look at concepts in the database. So we could look at some concepts that Noam Chomsky cares about in this particular paragraph. And then, so now we had 14 concepts in this text. I'm showing only 4 of them. And now you could say, well, but I also want to know that if Noam Chomsky talked about X, what are the other terms that he then also talks about? So one of the things that we do is we create a statistical relationship between terms. And we're not, well, actually, we're looking at the co-occurrences, but we correct the co-occurrence of the frequency of the A and the B term. And that allows us then to take these odds ratios here and show the words. So here you see if Noam Chomsky talks about South Africa, he also talks very much about Nelson Mandela. And by the way, find pictures that my Zoom screen is kind of doing weird stuff with my screen. So anyway, so I'm building slowly a complete kind of overview of everything that he ever wrote about. Of course, Noam Chomsky happens in other places. So there's some paragraphs that know some month later it appears. And I can compute similarity. So I could say, well, what is it similar to? And then I can keep going and going. Yeah. So this is kind of building up a total overview of all this work. But then how do I do queries over this? So for example, I could say, well, let's oh, sorry, let me go back here. Let me take a step. Let's just find a path from here to say Nelson Mandela. Yeah. Just to make sure that Nelson Mandela is a type, is a person. So now here we have a subgraph that describes part of what you were looking at. Let me take this out here. Go back here. So here's a part of the graph. I selected a little part of the graph, and now I want to see how often that pattern happens in the text. So I can actually take this pattern and put it in the query view, put it in the middle. So now you see the subgraph. And so what you see, book, chapter, paragraph, concept that recognize a relationship to another concept, which is a person. So basically what I could do is I can take all these constants and turn that into variable nodes. And then I also want to make sure that I only want to get the book back and maybe the person. And then I can run it as a query. And what I get back is people that are recognized in the various books. Yes, so the system automatically writes your Sparkle query, and here, just like in a relational database, you get your concepts back. So this is one thing that you can do building queries, or I can use semantic search. Yeah, so I have the book, I had, let me go back here. So when I look, for example, at a word like capitalism, then you see that this has probably a narrower. Yeah, so this, and then I can look at this. So I can keep going and going to expand the taxonomy that I loaded earlier, and I can use that to semantic search. So if I want to search not only on capitalism, but also on free market economy, and this is how you do this in Sparkle. Here you say, right, every concept that somehow matches the word war, then give me all the narrower concepts of that particular word war, and then find the chapters in the books that I'm looking for. And so when I run this query for war, what you see is the book, the chapter, and the concepts that I looked for. However, because torture is kind of a child of war, yeah, I don't literally search for only the war, but also all the descendant words for war. I hope that makes any sense. Okay, so let me continue. So this is one type of kind of document-based knowledge graph. We do this for regular companies, but you're never allowed to show their documents. So this is why we also actually built this particular knowledge graph. Well, let's continue. Yeah. So now let's talk about the second type of knowledge graph that we built. So, and I call it an events-based approach to integrate enterprise data. We've been working on this for the last 5 years, I would say, with Montefiore, sponsored by Intel and Cisco and HP. And as I said, we took data from close to 2 million people, 10 years of data, and put it into this big knowledge graph. And we take a lot of different types of information. So this is a typical patient like me, and I generate a lot of data. There is maybe I communicate with the hospital. I have a Fitbit that generates data. I know your genetic makeup. I know your family tree. There's devices in your body that generate triples. There's this big operational system in the hospitals called EPIC. It's 40,000. There's an Internet of Things in a hospital called the ICU where we look at 50 different types of data. There's tests, and I can keep going. But it is enormous amount of very, very different data. Yeah? So, and we have built processes to turn all of that into a simple model. We started in 2017 with the first model where we used machine learning on top of this knowledge graph. The first model was something that was built between Montefiore and the Mayo Clinic, where they looked at okay, I have patients in my hospital, which one do I need to intubate? If you don't intubate, they might die. If you intubate but you don't really need it, then you spend about $50,000 a day that you could have saved for something else. Yeah. So the question is, when do I intubate? And the Montefiore and the Mayo Clinic built this random forest model where they have about 46 complex variables that they take into account. Yeah. And where a complex variable is something like, give me the largest difference between the value for serum calcium level and the midpoint, and I can find the range of 0 to 20 for the last 24 hours. And so with these variables, we have this random forest model that is way, way better than doctors and nurses to predict if you need intubation. Yeah? Here you see just a little illustration why it's so hard for a doctor to actually make that prediction himself, because this is just 16 of these 46 variables. And here you see kind of a scatter plot or from the study where you show this is the mortality prediction. Here is the actual scatter plot for the data. For example, here we have glucose levels. And point being, no doctor can look at 46 variables, but the machine can easily do that. Then what happens now, and this is kind of unique, we can now compute every several minutes, go through all the patients that are currently in the hospital, we'll take all these variables into account, and then basically the doctor, when they go to the Epic screen, see a thing pop up, because of course the AI can say, hey, you need to intubate. They only can make a suggestion. Otherwise the FDA would never approve it. And then the doctor can say, well, it's not my patient, or I don't think he needs it. Or you can do a lot of things as a person then to actually make the real decision. And so this was the first one. Now I have models for sepsis. We do outpatient appointments. And all of these things actually involve machine learning. And one of the cool things is that when you do your machine learning work, you always get outputs, and we put the outputs back into the knowledge graph. So we kind of built learning systems. Yeah, that's one of the nicest things of the knowledge graph that we built in this particular case. And so now what you see here is all these different types of analytics. So normally, when you want to do all these different analytics, you get a whole IT team together and start working to make sure that you can do your analytics. But for every analytics, you usually have to get another IT team to get the data together. So the whole point of our knowledge graph was that we only one time do an ETL of the source systems into our knowledge graph. And then every analytic we can do, we can start doing in less than a day, just using the same data shape of the data. And so what did we do? So somehow relational databases rotted our brains, and we think it's totally normal that I, as a patient, can be in the enterprise data warehouse in, say, 4,000 different tables and 20,000 columns. Yeah? And so if I ask you, the guy from the enterprise data warehouse, hey, can I get can you show you all the data about me? They will laugh and say, well, no, you can't do it. That's way too hard. And it is, because the relational model for complex data is way too complicated. And so we flipped the data model where we take our core entity, which is the patient, and then everything that can happen to the patient, we turn into an event. Yeah, where an event can be a test, check in, check out, diagnosis, procedure, medication, and what have you. But all these events have actually the same shape. They have a type, a start time, an end time, the patient, and maybe a few key value pairs that then describe the rest of the event. And that's it. And so the data shape becomes incredibly simple, and we still don't lose any information. So here, you guys now know how the graph works. So this is the data shape. You have a thing that is a person, and that person has an event, this is an outpatient encounter that happened at a particular time. And this encounter had a sub-event, which is a patient diagnosis. And the value of that event is allergy to peanuts, which is a billing code that hospitals use, or an ICD-9 or ICD-10 term. And this gets mapped through another object to integrated taxonomy. So in the healthcare and the life sciences are way ahead of the rest of the world in terms of building taxonomies. Because if you're in the life sciences healthcare, it's really, really important that you give the same name, the same thing. Yeah. So they were earlier than anyone else making these huge taxonomies. The problem is there's so many of them that we then had to do work to integrate them all together. But now we have this nice integrated taxonomy system. And so if you look at my screen, to the left is all coming from the enterprise data warehouse and HL7 streams. And to the right is about the 350 million triples that describe concepts in healthcare. And by the way, the yellow things are alternative and synonyms for diseases, so you can use that for your text analytics. Anyway, so now once you have that data, your queries, because the shape is so simple, your queries become incredibly simple. So for example, if you want to do a query that says how many patients have gallbladder calculus in 2010 or later, then this would be part 1 of 3 of a SQL query that you probably can't write in less than a few hours. Whereas in a semantic graph database, you can just draw this query. Yeah? You can say, is there a person had an encounter with a diagnosis that corresponds to a concept that exactly matches gallbladder calculus, and it happened after 2010. And I just push the button, I get my sparkle, and I get my answer back. Yeah? So, and the same shape of query you can apply for, hey, for bills that were not paid, or did someone check in after a certain date? I mean, the shape hardly changes, yeah, because the data model is so simple. And then the other thing is, I mean, if I ask someone, give me all the data in the enterprise data warehouse for me as Jans Aasman, they laugh, because we use, well, one of the things that Danny didn't talk about is that triples actually have 4 elements. The 4th element is called the graph or the context. And so in our system, the 4th element of every patient triple has the patient ID. So now, and again, for you guys, if you don't know, Sparkle doesn't mean anything, but with one line I can say, select everything about this particular patient. Yeah, and I get my data back. Now, a UI designer that wants to do something with this would go crazy, because now he has to recreate this from scratch. So what we actually help with is we also can give it back as a JSON or JSON LD object. Yeah. And then finally, I talked about how we do analytics. I already showed you the integration example, but just for fun, I'll show you another example. So imagine 2 million patients, 10 years of data. So you can do very cool things like look at the core occurrence of diseases, yeah, corrected for the frequency. And so let me just give a little demo of that, if my system is still up and running. Now this is Chomsky.
So Hans, we have about 5 minutes.
Yeah, that's all I need. Yeah. So so imagine this, you have all these patients, you do a run over all your data through every encounter, and you compute how often 2 diseases or disease procedure or medications go together. Then you correct for the total frequency, and then you get a number that says how surprising the co-occurrence of 2 phenomena is. And so, for example, now we can look at what are the highest related symptoms for allergy to peanuts. And so this is the Sparkle query. You can, by the way, also do it as Prolog. I run the query, and then my system ran out of, okay, let me just in 1 second see if I can get it up and running in 1 minute. It's then really bad, because otherwise, let's see if I can do this. Probably better. So the point being that I can now predict for every ICD-9 term, for every billing code, for every procedure, for every medication administration, what are the most related other things? And I can start thinking about causation in a knowledge graph. So for example, here is my query, odds ratio for peanut allergy. Yeah. And I can run it as a query. And now this is the Sparkle query, and I can see here, and I can see that allergy to peanuts, yeah, is related to, say, dermatitis due to food intake. So if you have allergy to peanuts, the chance that you have dermatitis due to food taken internally is very high, 210 times higher than you could expect according to chance. And 2 types of asthma are 60 times higher. Then we have another dermatitis that is 37 times higher, etc. You could even, if you wanted to, look to see if there were more relationships between all of these. But for now, here, okay, I can do this. And you can actually ask the database to look at all the other relationships that you might have in this particular database. And you do a shortest path between each of these steps. And then at some point, you see that these diseases or symptoms are also highly related, but they're all kind of in the same category. Anyway, I don't want to belabor this point anymore. I just want to close up. And go back here. And so I hope that you guys have a lot of questions later. My takeaway is that building knowledge graphs is great fun. It's one of the greatest things, fun things I've done in my life. And very important that everything in all the knowledge graph that we build start with taxonomies and ontologies. Because if you don't have standards for the names of the nodes you have and the links between the nodes, you can't play with other knowledge graphs. And I think that was also the point that you have one standard for this information and you can start sharing data. Anyway, that was my, I'm done, Vinay.
All right, thank you very much, Hans. You could review the questions in the chat. Some of the questions are directed at you. Maybe you can just answer them directly in the chat.
Yeah.
Okay.
Yeah.
So we'll have Michael speak next. Michael, would you like to share your slides?
Yes, and I can also share my video if you make me a call.
Sure.
I just can do it right now in Zoom.
Yes.
Because the host has stopped it, but I can share it if you allow me to.
Do I have to do something to do that?
Maybe you need to make me a co-host, and then I'll be able to share.
Just a second. Let me just. Michael. Okay, I made you a co-host.
All right. Yeah, you can see me now.
Yes, we can see you.
Perfect. Hello from the other side of the globe. It's Germany. It's almost 3 a.m. here, but when science calls, I'm always in. Yeah. Can you see the slides?
Yes, we can see the slides.
Perfect. Right. So my name is Michael. I'm from TU Dresden, from Germany. I'm a senior research scientist, and we're working on knowledge graphs and conversational AI agents and NLP and graph machine learning, all this stuff. So, and in this talk, I'd like to give some broad definition and a description what different communities understand by knowledge graphs, and give a bunch of definitions, talk about a bit of different representations, because I already saw in the QA indicate part different questions on different representations like vector representations. And we also see how KGs are perceived from different communities, and then we'll try to come up with some shared understanding of what is the knowledge graph, how people define them. So, giving a definition of a knowledge graph is actually quite hard problem, because there are manifold of them. They span from very formal ones, like that one, like mathematical ones, when you have given entities and relations, then you define a directed multi-relational graph that comprises triples, SPO. Then you have less formal definitions expressed by words that you can find in different papers, something like that define a schema or contain various topical domains, then or KGs contain abstract schema instances, or some every RDF or labeled property graph or whatever RDF star graph is a knowledge graph. And well, the fact is that all of them are correct, but in different contexts. So we'll start our analysis from some ground truth, and by that ground truth we can consider KGs as some graph structured world model. So what we understand by a world model, well, we can say that those are our domain of discourse, which consists of entities and relations. So on the right side, you can see, I think it dates to 2016 part of Linked Open Data Cloud. So each of those bubbles is its own small world, is its own domain. And they define their own entities and relations. Well, some of them might be shared due to shared vocabularies. And you can see in the legend that the red part, it's more like life sciences data sets. And the brown one is about government data, and grayish is about social networking data. So all of those small bubbles are small knowledge graphs, you can say. So the question is, how do we encode those world models and those entities and the relations? And we have two polar approaches, pretty different. Those are symbolic representation and vector representation. With the symbolic ones, we use symbols to encode entities and relations as, well, some strings. Whereas in vector representation, we put subjects, predicates, objects, everything we have into some high dimensional vector space. And symbolic representation is often used in logic when we try to build some logical inference systems. It's also pretty heavily used in databases and data integration systems. Whereas vector representation is like the way to go when you work with the computer vision or NLP applications. Plus, there is also a like orthogonal dimension to those as small souls that you can add to your knowledge graph. And those are different open world or closed world assumptions that you will say. For instance, open world means that everything which is not explicitly stated in a knowledge graph might be truth. It's not false by default. And temporal evolving means that your facts can change their truth value over time. Something like a president of a certain country, he's a valid president only within a certain period of time, then the next guy is the president. And that's actually problem of many first attempts to build knowledge graphs. Then when they try to list, so say presidents of a certain country, then they will have like 40, 50, 100, whatever, how many people there were presidents, but they never specify who is the actual president. And that's a big shout out to Wikidata that it is actually possible to annotate who is the current president there. So starting with symbolic representation with triples, here is a short example of Robert Downey Jr. and some of the cherry-picked data about him, that we encode some knowledge where he was born, he lived, where he lives, and which movies he was starring. So for instance, yeah, we use triples here. We are directed edges and entities are parts of the triple. So for instance, Robert Downey Jr. born in New York, and we can write it down in this symbolic form, where DBP, it stands for DBPD predicate. DBPD is one of the knowledge graphs similar to Wikidata. So it is just to separate the namespaces. That's why we use DBP. And describing all those edges symbolically, we construct such a graph, which consists in our case of 8 entities and 6 different relations. So going then to embedding, it's a much more novel representation, I would say. So we try to place entities and relations to some high dimensional space into an embedding space. and to map our symbolically represented entities and relations to a high dimensional space. So for instance, entities will be contained in a matrix, in a tensor of certain size, where it will be of size actually number of entities by some dimension, like 200 or 1000. So here I try to give a short example what we can have as a two-dimensional knowledge graph embedding. For instance, we have some function which maps our entities to our space, and this function works in that way that it places similar entities, semantically similar entities, close in our embedding space. That you will see that entities which point to Robert Downey Jr. with the relation starring, they actually group together in the embedding space as well. And that's the big advantage of those different KG embedding algorithms, that they can build pretty descriptive representations. Of course, this is, you will never receive such a well-built picture, because most of them are like 200 dimensional, 1000 dimensional. You always need to use some dimensionality reduction algorithms. But in a nutshell, we want to build something like that with KG embeddings. Yeah, so then we go to different points of views, how different communities understand knowledge graphs. We start first with the logic, and we start with logic programming and like data log or prolog style. One of the classic approaches which heavily used, for instance, in databases. So we define first symbols, our entities, like Robert Downey Jr. or New York or San Francisco. And we also define several predicates, like different arity. In our cases, those are binary predicates like lives and born. And then we build our data set, or, well, it's actually a graph, but theoretically it's called data set, which actually is comprised of those facts that Robert Downey Jr. lives in San Francisco, but born in New York. So from that perspective, knowledge graph is a logically consistent collection of facts. So we go a bit further to more strict logical formalisms. We call those description logics. And lots of ontologists in semantic web use different type of description logic, or some logical formalisms like RDF or RDFS. And our knowledge graphs there, when trying to be built with DLs, usually they consist of three main parts. The first part is T-box or schema, so you can call it ontology, which specifies relationships among abstract concepts. For instance, successful author is somebody who has at least one notable work, and this is a bestseller. On the second level, we have instances, facts, assertions, also called A-box, but we can call it like factual information, instance data, which actually defines a real word, fact word, a triple, like Stan Lee is a successful author, which will be a triple too. And finally, we have R-box as a describe different restrictions and constraints, where we can say something about predicates and their hierarchy and their constraints. That is, will be notable work as a subproperty of created. So from that perspective, knowledge graph will be a logically consistent collection of axioms. And I try to outline here the difference between ontology and a knowledge graph. That ontology is more of a, well, you can consider it as a T-box of our KG. So it's mostly works on theoretical level, on the concept level, whereas knowledge graph is a box is assertions, our facts and instances together with the ontology. So that's the, in my view at least, the main difference between ontology and a knowledge graph. So then we go to databases and data integration. Knowledge graphs here help us to create a unified view on heterogeneous sources. Here it might be structured sources. And we use semantic data integration mechanisms to lift those heterogeneous data sources like JSON data, like XML data, CSV data, and transform them to a knowledge graph. So you will query the knowledge graph as one logical source, and on the background, it will rewrite particular queries to particular source. That's the big power of data integration and the federated mechanisms, as Danny told. In Wikidata, you can do that when you can query link geodata directly from Wikidata. But this is very cool. And a short example on a small table that you can transform one table, like author notable work, date of birth, to a graph where entities will be cells and relations will be column headers. So for instance, Stan Lee, Iron Man, and date of birth. So Stan Lee and Bob Kane will be instances of type author, and they will have two different relations, notable work and date of birth, and the data will be taken directly from the table. To drink a bit. Sorry. So then we go more to AI-ish field, more to vector representation of graphs. One of the examples from computer vision are scene graphs. So our task here to build a graph from objects which we can identify on a picture. So given just an image, you pass it through your fancy computer vision algorithms, identify objects, do some segmentation, masking, all this stuff. And in the end, you have a collection of objects which you would like to arrange in a graph with a certain relationship. For instance, man will be riding a horse, but horse is actually in front of a mountain. So mountain is behind a horse. And you would like to infer those relationships from the picture. So actually, it's an interesting question, where do you get those relationships? Most of the time, they are in the data set as already existing relations. I need to classify or rank the most suitable ones. Though it's much more interesting, of course, to derive those new relations which do not exist originally in a graph. That actually man wearing a hat, or what can be other relation between man and a hat. How can you relate man and a hat other than with the verb wearing? Then more to NLP. So we're working in NLP, so we do, I will give a bit deeper look here, since it's one of our main specializations. So the first big thing is how we can build knowledge graphs from text. And here is the information retrieval part. Since those sources are pretty unstructured, so we need to resort to classical NLP and IR methods. For instance, to parse our sentence that Albert Einstein was a German-born theoretical physicist who developed the theory of relativity. We know that there are some named entities like Albert Einstein or German-born, and there are implicit relations that we would like to identify from that sentence. We would like to build a small local knowledge graph that Albert Einstein was born in German Empire, and his occupation was theoretical physics, and theory of relativity is actually part of theoretical physics. So there are two approaches how you can do that. You can extract them directly from the text, do not have any reference KG like Wikidata on the background, or when you have some KG in the background, then you can have some additional signal. And that's actually the content of some with the following slides that you can do better named entity recognition and linking and disambiguation with knowledge graphs. So for instance, that's the excerpt from Wikidata for apples. So when you have different questions or sentences, who is the CEO of Apple, or Apple belongs to which genus, and you have actually quite a lot of entities that share the same surface form or like label in Wikidata. You have Apple as a fruit, you have Apple as a musical album, have Apple as a record label made by Beatles, and you have Apple as a producer of hardware. So you see that they share indeed the same surface form, but as Danny told, they are uniquely identified with different QIDs. So given those descriptions and their synonyms, we can map those or use them as additional signal to identify the context. And who is the CEO of Apple? This apple will definitely not be the fruit of an apple tree, and probably not the musical album. In this sense, we would rather put Apple as this apple as a producer of hardware. Whereas for the second sentence, Apple belongs to which genus? Well, you can have genus of fruit. So we'll rather use Apple with the ID Q89 here. I'm a bit short of breath, that's why I'm a bit talking a bit fast, sorry. So the next task is relation linking. It's a bit similar, but instead of finding and mapping named entities, you'd like to map relations. So actually in all those 4 sentences, the verb points to the same predicate in a knowledge graph. And KG, in this case, Wikidata can provide us not only with the list of those relations, and there are like 6,000 different relations in Wikidata, more than 6,000 already. You also have surface forms like synonyms. You can also have a lot of hierarchy and constraints on those predicates, which are extremely useful in mapping those and extracting those from text. So acted, casting, starring, has acted will eventually be mapped to a cast member, to P161, rather than to performer, which is 175. The task which kind of requires using both name entity recognition, linking, and some more mechanisms is question answering. And this is a question answering over knowledge graphs when you have a background data and you answer questions to it in natural language, like how many Marvel movies was Robert Downey Jr. casted in? And you want to translate this query to a Sparkle query. So this is a Sparkle query to DBpedia, for instance. And that's actually the cornerstone of all the KGQA approaches, how you transform such a query, such a question to such a query, that you would like at first to get all Marvel movies, then you'd like to get everything starring Robert Downey Jr., find an intersection and count the power of this set, how many entities are there, and the interesting thing that sometimes there is no one-to-one label or string mapping, that how many Marvel movies will actually be translated with something with triple pattern URI of DBP Studio, Marvel Studios, and the same with similarly different with Robert Downey Jr. And then you would like to put some count. You have to infer from the question. You would like to have a count here. So all those approaches are pretty different and cumbersome, but so right now they can answer pretty complex queries over those enormously large graphs, including Wikidata. Last but not least, it's actually one of the most interesting parts here, the newest ones. It's a language modeling. So you probably, if you work in NLP, you probably know that language models pretty much occupied all the NLP research world, and everybody's using pre-trained language models for downstream tasks. And by language model, we understand the system which predicts a word in a sentence given just half of this or all previous words in a sentence, and we call it a unidirectional model like GPT-2, or when it predicts a word giving the whole context, the whole sentence, then it's a bidirectional model like BERT. So those traditional language models, they are trained only on texts, on large corpora, such text unstructured sources, we call them. Something like Wikipedia or Reddit or Common Crawl, those are enormously large, like hundreds of gigabytes of text. And the systems are pretty good. You see that from year to year, they achieve even better numbers in NLP benchmarks like glue or superglue. And you can fine tune them for a manifold of tasks. So the recent emerging trend here is to actually plug in a knowledge graph here because it provides you with precise facts that Robert Downey Jr. actually had a character role of Tony Stark and Tony Stark is a character in the Iron Man movie. And you don't need to scan through the whole Wikipedia or rather get this triple already from the graph. So along with those precise facts and entities with the relations, you also have a great bunch of explainability issues solved, because you can point to a particular triple where you got this information, where you got this fact that you predict that this mask token shall be transformed to a particular, well, to another token, like here, portray Tony Stark. So this is a very fast growing field, and we expect quite a lot of papers in this year and next year for language modeling. Yeah, so finally, in conclusion, what then can we understand by knowledge graph, starting from that graph structure world model? So we know that it consists of entities and relations. It's pretty much shared thing within all tasks, within all communities. And those entities and relations can be organized in schema of different logical rigidness. You can have either pretty hard, pretty strict logic behind, like OWL or something else, which will give you a strong logical background. Or you can have just a collection of facts without logical schema. Then you can have, of course, different representation of those symbolic vector, and they are reused pretty much. You can switch from one to another for different tasks. And also two big things which are more important for other communities, like from humanities and from social sciences, that you can have multilinguality out of the box. Since you have abstract entities which are pretty much independent from string labels, so like QIDs in Wikidata, then you can attach how many, whatever, many language labels, like 414 languages in Wikidata. This is pretty cool. You can have all 414 labels for only one entity, or for all of them. That's very cool. And also each fact, most of the times, is tracked down to a particular source. So that's a great part for provenance and a great deal of explainability that KGs bring to machine learning world and other applications. I think that's it for me. So thank you very much. And I'm happy to take some questions here.
Thank you, Michael. So Naren, have you scanned the questions list? Are we ready with our first question?
Sure. So thanks to all the speakers in these uncertain times. The topic was amazing. We have 60 questions. A lot of them have been answered. But why don't we sort of start with a couple of basic questions, and in the meantime, if some of the panelists want to answer some of the questions live, they can do it. So why don't we start with a question from Jade Razagi? How do knowledge graphs and ontologies differ from each other? Maybe we can start with that.
Okay. Does any panelists want to answer this question?
Mika,
Danny, go on.
Yeah, no, I wanted to actually say Mika had this in his presentation. Technically, like academically, I would always say that knowledge graphs and ontologies are actually the same thing. But pragmatically, this is not a very useful answer. Pragmatically, I would always say that ontologies are actually formal specifications of the labels and graph patterns that you use in your knowledge graph. And this formal specification allows you to do the inferencing on them. So it basically says things like, oh, those two labels are related in this way, or this label is symmetric, and so on. And then the ontology defines the set of labels that you can use in the knowledge graph. But I'm happy to hear if Michael has a different point of view, or Hans.
Hans, do you have an opinion on this?
Can you ask the question one more time? Because the way Danny answered wasn't entirely clear. Can you ask the question again?
Sure. So how are knowledge graphs and ontologies related to each other or different from each other?
Oh, okay. Well, it depends a little bit. So if you take a free-form knowledge graph that I described with the Chomsky knowledge graph, you can get by with not building a real ontology. But if you are a big bank and you want to make a 360 view of your customers, and you need to go to hundreds, literally thousands of subsystems, then you better start with a formal ontology of all the important concepts that are important for you as a bank. You can't be free float that. You really have to be very formal about that. And then you link those ontologies to your data sources, and then you start building your knowledge graph. And then it's really, really super important that you have a very strict ontology. So it depends a little bit on the type of application. Yeah, but does that make sense?
Yeah, I think it does. And I think Danny explained it beautifully, and it also echoes what Michael said in his presentation. So yeah, I think that answers the question for me. I don't know, Mike, do you have anything further to add to that?
Yeah, actually, disambiguating those terms, then one should also ask about vocabulary. Like we also have vocabularies, which like schema.org, what is it? Is it an ontology or is it a vocabulary, or it's just a bunch of entities and relations they can use for annotating your website? So conceptually, those are very, very similar, but practically, I would agree with Danny that yes, ontologies are something for describing abstract relations between some concepts and your relations, whereas knowledge graph is something more physical, more like real world stuff with the real facts.
Cool. So
why would a formal description of a credit card, for a bank application be too abstract? I mean, for the bank, it's the most concrete thing in the world. And that makes sense.
Well, I think in my understanding, the knowledge graphs are dealing with instance level information, and ontologies are dealing with class level information.
Yeah, but your knowledge graph is chock full of classes. Yeah, the instances have classes.
Right.
Whether you explicitly represent the ontology in a knowledge graph, that is something else. Maybe you only build an ontology to build your shackle for shapes that you then use to validate the data that you let into your knowledge graph. I mean, you might not even want it in your knowledge graph, and maybe you're not doing any inferencing, but still, it's very important for big organizations that you're very strict about what you let in.
Right.
Well, on this page, then I also actually have a question to Danny, and it's very well connected to the topic of ontologies and logical formalisms. That, for instance, in Wikidata, there is the data model is quite more expressive than RDF. I would say that there is no clear separation between classes and instances in Wikidata, and any entity can be at the same time as subclass of something and also instance of something. So the question is, do we need any strong logical formalisms for such large scale, Wikidata scale graphs, or rather have some room for a mistake and do not punish user for entering some information which might not be logically consistent on the first side?
Yeah. So I'm a great fan of having inconsistent data and being able to capture inconsistent data, particularly in a knowledge graph of the size of Wikidata or most realistic knowledge graphs out there, because you usually have a lot of people working on it coming from different places. So you have a lot of data sets trying to bring them together, and it's super unlikely that the stuff will be consistent the whole time through. So for Wikidata, we obviously couldn't assume that everything will be consistent always. And we prefer eventually consistent models where the users kind of use maintenance scripts and bots to clean up stuff if they need to be cleaned up or not. But in the end, the Wikidata is like Wikipedia. It reflects what we know of the world, what is published about the world. And that is inconsistent because the world itself is not inconsistent, I assume, but what we know of the world is definitely inconsistent. And we need to be able to capture it and represent it. And this is why we opted not to have a strong ontology in this. Having said that, I'm still a huge fan of ontologies and strong formal models because they can help you immensely to find errors as long as you don't assume that they are the absolute truth. Like you can use them, you can find the inconsistencies and go through them, and they can be extremely helpful for that. But in the end, that's what they are. They're theories, they are models, and whether your data fits to it or not, it's a different question.
Right. Okay, well, I think we should move to the next question. Naren?
Sure. So there's a question by Edgar Velasco. What does it mean for a knowledge graph or a semantic graph to be acid?
As I understand, acid are the properties that are usually associated with transactional databases, right? And unless you are using your knowledge graph for transactional purposes, the use of acid properties may or may not be that relevant. Hans, do you have any opinion on this?
Well, I brought it up.
Oh, you brought it up, okay.
I think this relates to the previous point, is that you have knowledge graphs that go from something like Wikipedia, yeah, on the one hand, but it's rather informal, to knowledge graphs that are built into in an enterprise where it's really important. I mean, where it's a part of a production process, and you can't have errors like in a hospital. Yeah,
right.
So you everything, you can have everything in between.
Right.
And so it depends on the level of formalness that you require of your system. And yeah, if it's in a bank or sometimes in a hospital, you want ACID data, and sometimes you don't. In my Chomsky graph, I don't care at all. Yeah.
Right.
Cool. So there are a lot of questions around how to create a graph, how to evolve a graph, how to implement a graph, data structures. And for that, we specifically have a lot of lectures in the future. So please check our page. As a next question, there are some specific questions about some presentations. So this one is for Hans. Because the audio was not working, someone has asked, Hans, could you please explain the odds ratio thing again? How does this odds ratio thing work? The mic was not working properly at that moment.
Yeah. Well, you can look up the formula on Wikipedia, but basically think of it this way. You're computing the co-occurrence, whether it's words in the text or diseases in patients. So how often does dermatitis and peanut allergy go together? You get a number. But the problem is that in this sea of information, the co-occurrence is very low, unless you correct for the fact that dermatitis doesn't happen that much in the hospital data and peanut allergy doesn't happen. And suddenly that number becomes really big, yeah, compared. So basically, yeah, okay, I think this is enough. The Wikipedia will give you the exact formula for odds ratio.
Okay, thank you. This probably is a question for Danny from Lars Hansen. Is there any work/projects mapping Wikidata to a labeled property graph?
So the Wikidata model really fits a property graph really well. We needed to actually torture RDF a little bit in order to make Wikidata fit to that. The property graph model is a slightly more natural fit, but it's also not perfect, mostly because the properties in a property graph model, when they have further annotations, can only use literals and not entities. So this is a bit painful again. So what we did is kind of, we translated the Wikidata data model to RDF because it does fulfill all the questions, and not to property graphs yet. But having said that, there is work on, there are a few people who want to see if how good property graphs can deal with Wikidata. And I would be super happy if someone would set up a system that tries to do that so we can see how well it works. Because in the end, for Wikidata, we're not particularly married to a certain technology like RDF or property graphs, and we take whatever works. And we are currently straining the Sparkle endpoint, the Glaze graph that we have, quite a bit. And I would be happy if there would be alternative. But also, having said all of that, I don't think the difference between property graphs and RDF is actually big enough to merit too much discussion, to be honest, unless you are in this particular field. In the end, they both can support many different use cases and can be used in this almost interchangeably for most of them. So I hope that helps.
Okay, there is another interesting question here. Somebody asked that if an ontology is essential for a knowledge graph, then are machine learning and NLP aimless because they don't assume the existence of any ontology? So could any panelist try to take that?
Well, I mean, you can make an ontology. Say you do, you have your patient data, you do analytics, yeah? So actually what we do, when you do an analytic, so you have your knowledge graph of patient data, you extract a feature vector of the features you need for your analytics, then you get your result, and then what we do is we actually store the whole context of the analytics that you did. Who did the analytics? Yeah, when did we do the analytics? What was the data that it was used? Down to the result, and we store it in the database itself, and we have an ontology for the results of machine learning data. So we actually have an ontology on how you store the metadata for analytics and how you store the results. Yeah, so they go beautifully together. There's absolutely no conflict or at all. If that makes any sense to the person that said the question.
I think the question was if a machine learning or NLP program does not assume any ontology, is it aimless?
No, you can add anything you want. You can say in the semantic web whatever you want to say. Yeah. So if you want to do an analytics and you get a result and you just kind of without an ontology, you want to put it back in the knowledge graph, you can do that. The problem is if you do it the next time, do you remember how you did it the last time? Yeah, and ontology helps you remember how you want to get your data in the database. Yeah, so you can later do queries over it. So if you feel, if you're just working on your own and you're the only person that works with the knowledge graph, then who cares? You can just do your analytics, put data back in the knowledge graph, create a learning system, and you in your head have your ontology of how you want to represent the data. Right. If you work in a team of people, then you better have an ontology of how you store your results. Otherwise, other people can't do the queries over your results.
All right. Danny, you have a take on this?
I have, I'm not 100% sure I understood the question, but I have the feeling that whenever you do NLP, you basically necessarily have some ontology underlying it, because natural language always comes from humans, and humans have an ontology. So sure, not in the formal sense, obviously, but it's almost like you have this in the background whenever you do that. So no, I have to think more about it. Sorry. Let's stop this.
Okay. Naren, we have a next question.
Yes. So since we have like only 10 minutes left, there's like a generic question on limitations of knowledge graph. I know we have the last lecture, which are like open research questions in knowledge graphs, but maybe this panel wants to take a stab at what in your opinion are some limitations of knowledge graphs today?
There are plenty of those. One thing that we struggle in Wikidata quite often is, for example, knowledge graphs are not really good for tabular data, for time series, and for large statistical data sets, for example, because that's where relational databases really shine. And that's okay. I mean, they don't have all to be in the knowledge graph. So if I want, for example, to have the demographic information of a country and all its city and so on over a longer period of time, knowledge graphs are not particularly well suited for that, and I would use a different solution for this. Also because this kind of data ends up with tons of triples, which just puts more strain in the system. The other thing is that knowledge graphs, putting stuff into triples is extremely limiting in your expressivity. And whenever you look at a natural language text, you will find that there are so many things that are super hard to express in triples. And if you take a normal sentence from Wikipedia, from a more complex Wikipedia article, like how does photosynthesis work, or what are the reasons for World War II, and you try to encode this into a knowledge graph, you will you will notice the limits really, really quickly. So basically the expressiveness of knowledge graphs is very limited. You can still answer a lot of questions this way, but not necessarily the most interesting ones.
Cool. Any other panelists?
Yeah, so another interesting question is, this is actually at Hans, which is their system provides a choice between executing Prolog queries versus Sparkle queries. Can he comment on what's the advantage of using Prolog over Sparkle?
I was actually wanting to reply to Denny, because I think that with triples you can express anything you want. Yeah, but having, apart from that, I do agree that time series data doesn't work well, and sensor data, putting that in a knowledge graph, yeah, you better use it in combination with something else. But I see that knowledge graphs always live in a family of other types of databases. But about Sparkle and Prolog, well, Sparkle is a query language, but not a programming language, whereas Prolog is really a Turing complete programming language. And in Sparkle, if you have your classes in a Sparkle query, there's only 3 elements, yeah, and you have to fit everything in that. Whereas in Prolog, you can have functors with as many with an arity that you choose, as many arguments that you want. You can write rules that you then use in other Prolog rules. So I see these, I mean, we're a vendor, we see Prolog queries that are 300 lines long, and I look at it and I think, oh my God, I mean, I would have written for subparts and repeatable parts of the query in other Prolog rules, and then I would compose queries, yeah, where the top level query consists of other subqueries, which consist of subqueries. But it's almost like creating domain languages that take important patterns in your data and simplify them in simpler Prolog rules. So, and there's a big difference is also that Sparkle is a set-based query engine in most triple stores. Yeah, so it's way more like a relational database, the way the queries get executed, whereas our Prolog is depth first. Yeah, so if you start with a constant and then follow the query, and you don't want all the results in the database back, then Prolog will be sometimes faster. Whereas if you say, give me all the patients that have this and this, and then in the next month got that and that, then Sparkle probably is going to be faster. But it depends. And if you want to build rule-based systems, you're kind of limited if you only have Sparkle to work with. But if you want to build a nice rule-based system in Prolog, I mean, it's actually built for that.
Okay, I think that's a good answer.
I want to, sorry, I want to go back to Jan's point on you can express everything in triples. Technically, that's correct, but it's I would claim that it's as useful as to say, well, you can code everything in assembler. By using higher abstractions, you can be much more effective. And as I said, like trying to express things like photosynthesis in triples would just be extremely painful. It's possible, but it gets to the point where a lot of the advantages that you have of knowledge graphs, the explainability, the editability, and so on, almost disappear basically. And some things on top of it that could compile the triples, just like we do it with with assembler, is very much needed. And I would say this is definitely a limitation of knowledge graphs because they're not really good at capturing this higher level macros or patterns or whatever you want to call them.
Well, that's fair enough. Another question I see here is that how important are so-called upper level ontologies for knowledge graphs? Does any panelist want to take a stab at this?
Speaking from experience at Google, top-level ontologies are extremely useful to find errors in your data and to guide the creation of the ontology, the maintenance. There's one point that Jans mentioned earlier, which was like an ontology helps you to be consistent with what you are in the usage of the ontology over time, because you have to formally specify the different terminologies. And with a top-level ontology on top of everything, you have the possibility to make clear whether if you're meaning a building or an organization or a person and so on very quickly without having to state it every time, because you can just connect to the top level ontology and then use that for finding errors in your data. So we found it extremely useful actually to have a little bit of top level ontology.
Okay, good. Here's another interesting question. How does model theory fit into knowledge graphs? Does any panelist want to try to answer that? To some degree, Michael answered it in his presentation.
Yeah, well, if by model theory, Yateni meant model theoretic semantics, then this is what description logics are about. If another connotation might be modeling in sense of business modeling, like all those UML family of languages and business process modeling stuff, then, well, there are many business related ontologies where you can model the processes. They look a bit sometimes artificial. I mean, they are pretty complex to understand. You rather like draw a UML diagram.
Okay. So maybe we can try to take one live question. There is somebody named Samir Merchant. I have unmuted him. Samir, do you want to ask your question? Maybe not. Naren,
okay. Yeah. Sorry. Yeah. Can you hear me now?
Yes. Please go ahead.
Yeah. So my question was in terms of the scale and the storage perspective for the graph, for knowledge graph build-up. How does it compare, like using RDF versus property graph? Dennis kind of touched upon it briefly, but is there a guideline that you can actually do, an underlying system that you can use for scaling the queries when it comes to knowledge graphs?
Okay. Does any panelist want to take this? Well, I would say that
I can take a stab at it.
No.
So, in some cases, when you make these 60 knowledge graphs, where you have a particular entity and you link everything to that entity, then you can make your data shardable, and then the sky is the limit. If you have a graph that is completely connected, yeah, and you can't shard it or do subgraphs, then you better buy a very expensive HP machine with a lot of memory. But if you did a shardable partly, then yeah, then the modern graph databases will help you.
Yeah. Yeah. So, and also I think I should say that we do have a session on graph engine architectures in the industry, which is I think session 7 or 8, where we will go into this more in depth. But I think we're already over time, and we should end here. So we thank everybody for showing up for the seminar, and we look forward to your continued participation. And I thank the panelists for their illuminating presentations, and we look forward to the future sessions. Thank you all very much.
Thank you all very much. And just for a reminder, the next talk is next week on how to create knowledge graphs. So that will answer a lot of the questions that are posted today. So this is an advertisement for next time.
All right. Thank you.
Thank you.